Okay, so now we're going to use the Mayer-Vietoris sequence to compute the homology of the sphere. So the d-dimensional sphere. Okay, and the way to sort of think about this is that if you think of the sphere, right, you can think of it as the upper hemisphere, the lower hemisphere, and then the intersection being the equator. Okay. So you write SD as the union of the upper and lower hemispheres. Okay, so let's say SD is the U union L, upper and lower, and then with the equator as the intersection. Let's call that A is U intersect L. Okay, so each of the hemispheres are balls, right? So each of the hemispheres are balls. On the equator is a sphere of dimension d minus 1. Okay. So what we want to show is that the reduced homology, or the reduced Betti numbers, so we will show that the reduced Betti numbers associated with the sphere dimension d, right, is equal to 1 if p is equal to d, and then 0 if p is not equal to d. Okay. So so obviously we need, because of the what we've done here, right, where in particular the equator is a sphere dimension d minus 1, you have to do this inductively, right? So you will proceed by induction on the dimension d. Okay. All right. So let's see what happens. Okay. So let me just sort of leave it's like the upshot. So let's look at the d equals to 0 case. With d equals to 0, the sphere is 2 points. Okay. So the reduced homology has rank 1. In dimension 0 and 0 otherwise, right? Rank 0 otherwise. Okay, so that's consistent with the reduced Betti numbers. It's like we have, it's like for, again, d equals to 0. Okay, so we now have this inductive hypothesis for d equals to 0 satisfied. Okay, so this establishes the induction basis. Okay, so for general D, right? What happens then is that the sequence looks like the following. You get okay, so you get 0, direct sum 0, because again, if we recall, part of the sequence involves the direct sums of the individual pieces, whose union is everything, but the individual pieces are balls, which have trivial reduced homology. So this part is 0. This of course maps to the union, right? So this is HP tilde of SD, which maps to via the connecting homomorphism to the lower dimensional part having to do the intersection. But the intersection, it's like of the two hemispheres, is a lower dimensional sphere. So this is SD minus 1. And then this again maps to 0 plus 0. Okay? So this is the sort of the relevant part, if you will, of the long exact sequence. And you just get something much simpler because, again, some of the homology groups, it's like in the sequence, are trivial. Okay? So that's saying that, so you really have that these two things are isomorphic to each other. So this means that HP tilde SD is isomorphic to HP minus 1 tilde SD minus 1. Okay, so right. So basically, when you go up in and you know that this thing is, okay, maybe let's just put the rank of this. So this means that beta P tilde SD is equal to beta P minus 1 tilde SD minus 1. All right. And then the point is that you eventually get to beta tilde P minus D, right, S0, right, which is the which is equal to 1 if P minus D equals to 0 and 0 otherwise. Right, which is of course equal to 1 if P is equal to D and 0 otherwise. Right, which is what we were trying to prove this before. Okay, so again, this is a sort of a nice way to show that you know, how you can use, it's like this Mayer-Vietoris sequence, it's like to compute the homology, it's like of you know, it's like more complicated objects, it's like from simpler objects. All right, so let me just stop here for now.